What exactly is a derivative? I know this question might sound silly or stupid, I know it, but the question is more fundamental. When I ask you what exactly is a derivative, I mean to say is it an operator or some physical quantity? Now, why am I asking this question? Because many a times in physics, especially in quantum mechanics, when we study quantum mechanics, in that we study about different types of operators, and in that we study about the derivative operator. And in mathematics also, when we study partial differential equations or ordinary differential equations, in that also we study about differential operators, right? Like this. Like we have a very famous operator, Nabla operator. So what exactly is derivative? Is it an operator or a physical quantity? Because sometimes when you study uh, slopes in mathematics, we write the slope as dy by dx at a given x. Suppose x is equal to alpha. Okay, and in the derivation of this derivative, we use this concept only, the concept of slope, right? So what definition we give? We give the definition as dy by dx or df by dx, where f is actually a function of x. Okay, so it is actually equal to the limit as h tends towards 0 of the function f of x plus h minus f at x divided by h, right? Now I'm not talking about left hand derivative and right hand derivative, just this is the derivative term. Okay, so over here it is actually the slope, right? This is actually the slope. So what exactly is the derivative? Is it the slope, or is it an operator? So it depends on what framework you are working. And what I mean by this, I mean, suppose you are given f of x is equal to x square, and now you have to find the derivative. So in this case, you will define d, suppose d, as the derivative operator d by dx, and you will apply d on x, sorry, on fx. So it means it is actually df, which is equivalent to saying, or it is equal to df by dx. And what does this mean? Now over here the pronunciation will not be df by dx, it will be d by dx, the derivative operator applied on f. So d by dx applied on f, right? Over here this will be the pronunciation, derivative operator applied on the function fx. Okay, so over here it is not df by dx, it is d by dx, or the derivative operator applied on the function f. Now what is the function? Function is x square, so it is d by dx applied on x square, and this is equal to 2x from the definition of derivative. Okay, So when you are defining it as an operator, you have to use it as an operator, right? For example, Nabla operator, when we use Nabla operator or del operator, we use the same criteria that we are applying Nabla operator on some particular variable. It can be a scalar or it can be a vector. Okay, like in my previous lecture, I'm making a series on special theory of relativity. In that I have discussed that in lecture number 2 and 3 I discussed about Maxwell's wave equation. So in that I have discussed about Nabla operator, because I had to discuss about Maxwell's wave equation. So for that I have defined Nabla operator. So in that, what we were doing, we were applying Nabla 2 on E vector and B vector, right? So same is the case over here. We are treating it as an operator, right? Now when I say dy by dx, dy by dx, right? Now it represents slope. Now what does it mean? When you were deriving the general formula for slope using derivative at a particular point, you are using this concept, right? Okay, so the concept over here is that if you are given a function and you need to find its derivative, you will use derivative as an operator. And if you have to find at a particular point, you will use it as a slope. Now still the question can arise, what if we are given fx is equal to x square and we have to find slope at x is equal to 2? Then what we have to do? Then you can again apply df. So it means that d by dx applied on f, it is 2x, and now at x is equal to 2, so it is 4. So now what? Now the case is that here fx is equal to x square and we had to find slope at x is equal to 2. So we use the concept of taking derivative as an operator, and we found out the derivative, and then we substituted x is equal to get the desired slope. Now this is also this is a correct and a valid method, right? Even if you don't use this method, you can use this definition that df by dx is simply the limit as h tends towards 0 of f of x plus h minus fx by h, right? Okay, and then you can substitute x as 2 and you will get your desired result. Okay, so what's the difference? The difference is on perspective. Either you, even if you take it as an operator, then also it's fine. If you take it as a slope, then also it's fine. Okay, because the meaning won't change. Okay, but many times when you take it as an operator, then it is more beneficial, like in ordinary differential equations and partial differential equations. Because if you don't take it as an operator, then while solving partial differential equation, you must be well acquainted with partial differential equations and ordinary differential equations, or probably at least with ordinary differential equations, to know that there's something which we use in which we take the inverse of derivative operator. If you don't know, please forget it whatever I'm saying, but if you want to know, watch that one shot in which I have discussed completely about ordinary differential equation. I had made that one shot like some months back. So it is like its name is ordinary differential equations in one shot. I discussed it some months back. Okay, so in that I have discussed about this operator, right? So once you start taking it as an operator, then it becomes more useful. Why? Because then you can take inverse operator also in this, and it becomes more beneficial, right? So at the end I will say that you can treat derivative as both a physical quantity or a slope, or as an operator, right? Now the process when you take the derivative, that process called differentiation, that has nothing to do with derivative. Remember this thing, okay? So my point is that it is both operator and a physical quantity depending upon the way you are using it. But if you are using it as an operator, don't say it as dy by dx. No, say it as d by dx applied on y. That is a derivative operator applied on y. And if you are taking it as a physical quantity, don't say it as dy dx applied on y. Say it as dy by dx. That's it, because now it's representing just the slope, right? So that's the whole point of this video. So exactly, derivative is both an operator and a physical quantity depending upon your need, okay? But assuming it as an operator is much more helpful, right? Let's solve some questions to understand this concept better. So suppose the question is fx is equal to sin x, okay? And you have to find the derivative of this function. So what will you do? Well, you will treat derivative as an operator, which we call as derivative operator, or in mathematical language we call it as a differential operator, right? So we'll use d applied on f, or d dx applied on f. So d dx applied on sin x is equal to cos x, right? Now this cos x is the function which we have got after taking the derivative of this function fx, which is equal to sin x. Fx is equal to sin x, and the derivative of this function is cos x, okay? Now suppose if I ask you to find the slope of tangent at x is equal to pi by 4, then what will be the answer? The answer will be very simple. Just substitute x as cos pi by, x as pi by 4, so you will get 1 by root 2 is the slope of the tangent, correct? Right? Okay. Now let's reframe this question. We have to find the slope of the tangent at x is equal to pi by 4 for the function fx is equal to sin x. Then in that case you can use the definition of derivative. And what's the definition? We will use it in terms of slope of a tangent. That dy by dx at a particular x is equal to, suppose, alpha, is the limit as h tends towards 0 of the function f of alpha plus h minus f at alpha divided by h, right? Here alpha is equal to pi by 4, correct? And now you can simply substitute the value over here. Let's substitute and let's see what we get. So we will have sine of alpha plus h minus sine of alpha divided by h. We will substitute the limit in a few moments, but let's first of all simplify this, okay? Now we know the expression sine a plus sine b is equal to 2 sine of a plus b by 2 times cos of a minus b by 2, correct? So now you can substitute b as negative b, so you will get sine of a minus sine of b is equal to 2 sine of a minus b divided by 2 times cos of a plus b by 2, right? Now I just substitute it over here. So this is a, this is b. So this is 2 times sine of a plus b, alpha plus h minus alpha. that is sine of h by 2 times cos of alpha plus h plus alpha, that is 2 alpha plus h by 2 divided by h. Correct? Okay. Now we have to solve this expression. Correct? And of course the limit is as h tends towards 0. Okay? This is h. Right? So when you substitute h as 0, then of course it will be a 0 by 0 case. But if you substitute h as 0 for cos term, this will become cos of alpha. So you can take cos of alpha outside. So you will get cos of alpha. In fact, you can take 2 also as common. So 2 will be taken as common times sine of h by 2 divided by h, right? And of course the limit as h tends towards 0. Correct? Okay. So now what we can do? We can divide it by 2 and we can keep 2 over it. Right? Okay. So this will become, now this limit will tend towards 1. So the final result is cos of alpha. And of course alpha is equal to pi by 4. So again from here we get the value of slope as 1 by root 2. Right? So this is so these are the two methods which we use to find the derivative. The first is treating derivative as a differential operator and then solving for the derivative, the function, the differential function which we get after taking a derivative, cos of x, and then you substitute the value to get the slope at that particular point, or you can use the definition in terms of slope to get the desired result. Right, now let's solve some more questions to strengthen our concepts. Right, let me erase this. Suppose there is a function f of x comma y is equal to x square y plus y sine x, right? Okay, plus let's take it as sine y. Okay, now you have to find the derivative, the partial derivative with respect to x and with respect to y, right? So how will you find it now? Okay, so let's see. Now in this, either you can use the concept of slope of the tangent, but over here it will become complex because not complex number, it will become complicated, I mean, because now we have two variables over here, right? So in this case, either you can use the definition or you can treat del by del x and del by del y as partial differential operators, and then you can solve. It will be very much easier instead of using the definition. That is del x applied on f is del by del x square y plus sine y sine x. Now just apply this operator on each term. So you will get del x is applied on x square y plus del x sine applied on sine y times sine x. Now since its operator in x, it's a partial differential operator in x, so that is why we will treat y as a constant over here, right? So we will get it as 2xy plus sine y cos x, right? And similarly del y, what we'll get as del y applied on f. So clearly it will be x square plus sin x times cos y, correct? Okay. So this is a very beautiful use of differential operator, right? Instead of using the concept of slope, you are just directly finding the function which you will get after differentiation, and then you can substitute desired values which will be given in the question to solve it further, right? So if you are given a particular point, you have to check at a particular point the slope or whatever, the change, the instantaneous change or whatever you want to check. You can just use this concept, you can take the derivative and you can solve it, right? Now if anyone asks me to find the slope at a given point, suppose 2 comma 4, I can simply substitute the values and get the answer. No need of using the definition of different of the derivative, right? We can directly use it as an operator and solve it, right? Now let me erase this and let's solve some more questions. Suppose you are given the position of a particle as a function of time 2t square. Let's assume it like this, okay? So now you have to find the velocity and acceleration of this particle. And of course it's x-axis, so of course it is if I write in vectors, it will be x vector is 2t square I cap, okay, right? So if I have to find its velocity, what will I do? We know that the derivative of position with respect to time is the velocity vector, is the velocity vector, correct? So it means that when the differential operator with respect to time is applied on the position, we get the velocity of that particle. And similarly, when you take the second differential operator with respect to time of the position, that is you are applying it on position vector, you get the acceleration, right? And suppose it is in multiple dimensions, suppose x, instead of x you have suppose r vector, and instead of taking 3 dimensions I am taking in multiple directions, I mean in multiple dimensions. It is given as r1 I cap plus r2 j cap. Let's take it as I1 cap and this is I2 cap plus R3 I3 cap and so on and so forth. Suppose there are n dimensions, Rn, I, n cap, okay. Now these represent different mutually perpendicular axes. So they are of course representing n different spatial dimensions, right? Of course we draw 3 dimensions as like this. I can't draw 4 dimension on a 2D plane. It won't be understandable. So this is basically, suppose this is I1 cap, this is I2 cap, this is I3 cap, right? Of course we represent it as I, J, K, but to explain this, because I have taken n dimensions, this is how it would look, okay? Now what is R1? Now this Ri is a function, is actually a function of time, right? Okay. So now let's find this is suppose dimension 1, this is suppose dimension 2, this is dimension 3, this is dimension n, okay. Now what is the velocity in dimension 1? So v1 vector is this expression, right? Correct? Right or not? Correct? Yes. So this is v1 vector, this is, so vk vector can be given as d by dt, that is the differential operator with respect to time applied on rk, right? Okay. Now what is rk vector? I have written over here r1. So rk vector is actually r1 rk times ik, the unit vector, okay, and rk is the magnitude, and this is the direction, okay. So this is the velocity in any dimension, in any special dimension, right? Spatial dimension, okay. And what is the acceleration? Alpha k vector is the second derivative operator over here, second differential operator applied on rk vector, okay. So this is how you find the acceleration and velocity, right, in any dimensional form, okay. Now what will the net velocity, what will the speed of the particle? The speed will be given as square root of all the vk square, okay, correct, yes. So this is how the speed will be given, the final speed, just like in case of three dimensions. Suppose this is vx, this is vy, this is vz. So the velocity, the final speed is given as speed is given as v square root of vx square plus vy square plus vz square, right? Like that we will use. Now coming back to the simple question. So just take the derivative. So 4t is equal to v vector and acceleration is 4 meter per second square. Suppose this is in meter per second square, okay, along I cap, that is positive x-axis, and this is also along positive x-axis. So this is velocity as a function of time. This is acceleration, since acceleration is constant over here, so we don't need to worry about that. And position as a function of time is given by this, okay. So this is how you apply it in physics. This is a very basic example actually, right? So let me raise this and let's solve some more questions. Suppose there is an electric field which has a vector form as, suppose, 2 x y I cap plus x square y j cap plus suppose z square x k cap, right? Now you have to find the divergence of this electric field. How you will find? Find the divergence of electric field at 5, 7, 10. Let's see. What do I mean by divergence? Well, divergence over here, I have defined already it in special theory of relativity in second lecture. You can watch that. I will just write a formula over here. It is very simple. This is Nabla operator. This is a vector. Dot with electric field. Right? So it is given as del x I cap right, dot electric field 2xy plus x square y of course j cap plus z square x plus k vector z square x, okay. Now just take the dot product. You will get del x applied on 2xy plus del y applied on x square y plus del z applied on z square x. Okay, so now just solve it. Now just substitute the value 5, 7 and 10. So 2 times 7 plus 5 square plus 2 times 10 times 5. So it is equal to 14. 14 plus 25 is 39. 39 plus 100. 139. What will be the unit? It is energy per unit. Sorry, electric field per unit length. Okay, so the unit of electric field is Newton per coulomb meter, right? Correct, because we know electric field F is equal to QE, right? So the dimension or the unit can easily found out from it. Okay, Newton per coulomb, and since there's a meter, so this is the answer. Okay, now if you want, we can solve one more question, right? Let me erase this. Now suppose there is a time term also involved in this equation. Suppose we have over here t square, rest these are constants. They are only changing with respect to space, right? Not with time. Okay, now what you have to find? You have to find Laplacian of E vector. What is it? Let's solve it. What is Laplacian operator? Or Nabla squared or Nabla 2, whatever you want to say. Del 2 by del x square del 2 del y2 plus del 2 by del z square. Correct? Okay. But actually it is not required to have a time dimension over here because it is of no use currently, right? Okay, so we have this expression. Let's solve it. So we have del 2 del x square applied on u vector plus del 2 del y square applied on e vector plus del 2 del z2 applied on e vector. Correct? Okay, so del 2 by del x square applied on this, what you will get? Once you take the first derivative, it will become 2y, and once you take the moment you take the second derivative, it will become 0. So it is 0 I cap plus, now with respect to this expression, it will become 2xy plus 2y j cap, 2y j cap plus, over there you will get again 0 k cap plus again 0 I cap plus x square y j cap. So when you take the second derivative, it will become 0 j cap plus 0 k cap plus del 2 del z square, right? So of course it will become 0 I cap plus 0 j cap plus 2x k cap, right? Now let's just club all these together. What you will get? So there is no I term. It is 2y j cap plus 2x k cap. So this is what happens when you apply Laplacian operator on E vector, right? Okay. So I have almost taken many questions regarding this topic, and if you have more doubts, let me know in the comment section, right? I will clarify all those doubts. Okay, so I think that's all which I should discuss in this video. If you have more doubt, please do let me know in the comment section, and I'm making a series on a special theory of relativity. Please to check it out, and Yeah, that's it for today. Bye bye. Take care.